So, hello everybody. I hope you hear me. Could somebody answer that? Yes, you hear me?
Yes.
Yeah, I can hear you.
Hello.
Oh, sorry, I had muted mic. Do you hear me, Angel, please?
Yes, Ian.
Thanks a lot.
It's fine. It's good.
Okay, so because we do not have too much time left, I will start to share the screen. Second, I will start to record. Please, I hope everybody is okay with recording this meeting so that it could be used more time. Oh, it's already recorded. Okay, it's good. Okay, so please, dear colleagues, thanks for joining today for the lecture on multiaxial fatigue. It comes from my experience with multiaxial fatigue analysis, which used to be my PhD topic some 20 years ago. And I would like to first thank to Cost Agency that they provided us funds for this kind of cooperation for promoting the fatigue analysis among people. So thanks for that, and let's go on. My name is Jan Papuga. I am a Czech living in Kunovice in Czechia, working there in a small private company or aircraft producer Vector, and simultaneously at the Technical University in Prague. And before that, I used to change quite frequently my working place, but now I'm stable for something like 20 years already. For a long time, I used to develop a practical fatigue solver. You can download it even today. It's a freeware, so do not hesitate to check it. But this activity should be superseded by a new attempt to get to program open source freeware code within a FABER project. I used to chair different workshops, even conferences, and I'm a member of editorial board of International Journal of Fatigue, I believe, thanks to my previous experience with multiaxial loading. Well, containing proportional loading, that's something which is quite understandable there. If we go to multiaxial loading, we expect that multiaxiality is induced by technically, for example, having two simultaneous load channels active. That means with changing load. And in proportional loading, this change happens simultaneously to reach the peak in the same moment. So in that moment, the stress tensor in one instant is a multiple of any other stress tensor, which is quite convenient for any calculation of multiaxial fatigue. In a non-proportional loading, it can be much more complicated. You see that there is a in parentheses proportional loading is identical to in-phase loading. This is not true to non-proportional loading. Non-proportionality is technically described as a moment when the individual components of the stress tensor do not correlate in time. That means individual channels are acting not in phase, in fact, which is an example here on the left side. This is out of phase loading with harmonic load channels. With this could be, for example, a 30-degree phase shift between both sinus waveforms. Here you see a trapezoidal course, for example, again out of phase loading. But the loading can be technically in phase, but for example, one load channel can be 2 times quicker, which is something called asynchronous loading, and this is the example here of this butterfly. But even this loading called as synchronous is something which is non-proportional, because if you try to analyze more circles in time, you will find out that principal directions are changing during such a simple loading. Just one is static, one is dynamic, and you are getting something which is not anymore proportional. What it causes is that the fatigue response is getting, say, weird, different. And what I will be showing to you today is basically above all focused on analyzing multiaxial fatigue strength, because of I deal above all with high cycle fatigue. And in that moment, if we have some equivalent stress to our multiaxial loading, technically we have a fatigue curve, a SN curve. We could get to fatigue life. But in our case, because we will deal with fatigue strength analysis, or more specifically to fatigue limit, in fact, we expect that the loading which is applied to the structure will be identical to equivalent fatigue limit. Yeah, so that means I will look for a case where the loading would be capable to get to fatigue limit. But if I miss that point, I go with larger stress amplitude. I can define something which is called fatigue index. It's a ratio between applied stress, some equivalent value, and the fatigue limit here. Now, I will show you my experience with validating and testing very many different multiaxial fatigue criteria. And for that, I had to build some practical means of comparison. So if we design to fatigue limit to infinite fatigue life, if it exists, we are checking that this damage parameter is in some way equal or rather lower than the fatigue limit. Yeah. Fatigue limit in our analysis will be related to some kind of axial loading, usually F-1, which means in push-pull, in bending or rotating bending. Now, if we use experimental data which led the multi-axial test case to fatigue limit or something resembling fatigue limit, then I expect that this damage parameter, which is a composition of different stresses usually, is identical to fatigue limit. This doesn't happen too often. It doesn't happen nearly any time. Yeah. So that means we define something which is called fatigue index error. This is equivalent stress minus fatigue limit divided by fatigue limit. This is basically a relative error in fatigue limit estimation in the direction of stresses and lifetimes. Now, what we can do with that, once we have this metric of analysis, we can set across large group of data what is its average value, what is the range, what is the standard deviation to show how scattered the results will be compared to perfect results. Average value is interesting. Delta Fi larger than 0 will mean that the prediction is conservative. If it is smaller than 0, it's non-conservative. And this statistical evaluation can be done on different data sets. Yeah, for example, here you see classification of the original data set of all experiments to cases with no mean stress, mean stresses with axial and torsion loading channels active, or biaxial loading, and so on. In that way, I can compare average, range, standard deviation, and so on. But if I look at the data overall, that means only in this column all, I can generate also, for example, a histogram of fatigue index error. And it shows, okay, for example, here, with fatigue index error between -5 and +5, I would get something like 50% of all data, of all results, of all predictions. So Technically, we would be quite happy if, based on Papadopoulos' proposal from 90s, we could get all all our prediction results to the scope of something like -10 plus 10%. That would be an awesome quality of fatigue strength prediction. This doesn't happen for any criterion today. And we are still speaking about estimation in stress direction. That means if we exceed the fatigue limit by 10%, it can have a profound value, a profound implication as regards the final fatigue life, for example. Because I dealt with these analyses for a long time, I generated a website representation of all data I used to have in that moment. This is this Practicum Experiments PHP website. There is some kind of evaluator. This is not active computation, just data from analysis in practice using different multiaxial fatigue formulas are gathered here. You can use some preselection or just some of the data and look what is the response, which can be useful for you if you have some specific industrial case to deal with. The issue is here that this large set, which is here something like 450 experiments, was later checked by me, and today we have a much better representation of a data set which is smaller, something like 300 data items. Mostly because we have found out that part of this experimental data are based on experimental results provided in weaker quality. We are not sure if there were some errors. We are not sure if there are trends which should be monitored. For example, the SM curves are built just from 3 specimens, for example. So such cases were abandoned, and today the final data set is smaller. And this still waits for real publication. Now, if we deal with multiaxial fatigue, we are looking for a way how to convert the, say, full tensor or just 2 stress components from a tensor to some equivalent value to which we can say this is equivalent fatigue strength or stress, or this is some compound value which I can compare with, for example, Basquin formula to get fatigue life. As engineers, we are tempted anytime to use those simple solutions. For example, here for signed von Mises stress. Von Mises, everybody know what is this criterion for static analysis of more complicated stress states. The issue of it is that the product is under square root, which means that if you apply it to a stress, to a load signal, we will end up with, which is symmetrical, around 0. We will end up with a stress signal, which is with non-zero mean stress and half the amplitude. So because of that, some kind of signing has to be applied. Here you see cases where, for example, it is signed by first invariant of the stress tensor. The trace of the matrix or of the tensor computed, you will check what is the sign, and based on that, you will set instantaneous value of signing this Mises stress to some modified value with asterisk. In Nastran or in other cases, you can also use other ways of signing, for example, by the outermost principal stress. If it is more compressive or more tensile, you can select the sign here. Once you have amplitude and mean value of the stress cycle over the period, you can use some kind of mean stress effect. For example, here I proposed Volcker formula. And here we can see what is the general outcome. For a large data set of more than 400 experiments, we have tried to build a histogram, and you see that basically it's extremely low. If I would check what is between the range of -10 and +10 percent of fatigue index error, I would get to 3, 18, 17, 27. I would guess a bit less than 50% of all data is in the desired location. For the other half of the data, about 200 specimens, we would get to results which are much more aside from the perfect results. In some cases, you see that something like 1/6 or 1/7 of all the data lies out of the box, out of -40% and +40% of the fatigue index error. That means you see that that's already something which is not applicable. With such a huge errors in stress estimation, that's basically equivalent stress estimation, nothing else. You cannot proceed with a computation on which somebody is relying. In MSc, fatigue used to be implemented something which is called MAPS criterion, maximum absolute principal stress. And when I was discussing that with guys here of a company selling MSc fatigue, before it was sold to Hexagon, they recommend me this criterion for a general multi-axial state. If we check it, what it does is that it goes through the stress period, computes principal stresses in every instant, and uses the envelope of maximum principal stress and minimum principal stress across the period. And from that, it computes mean value, amplitude, and uses again some mean stress effect evaluation. Here you see the output. It's generally as bad as for Mises. But if you go to MSc fatigue help, you will find out that they recommend to use these simple criteria above all for proportional loading. So to be fair, I have tried to modify the input and use only those tests which are which are clearly proportional or uniaxial. So from the whole data set, we have only 190 data items, which are either uniaxial or proportional. And here, if I check the results, okay, I will get to 40. It's slightly better, I would say 51%, maybe 52% of all data are lying in the desired location between minus and plus 10% of fatigue index error. So basically, these simpler criteria as principal stress, as von Mises, they do not work at all in multi-axial stress space. We have to find out something better. And now, if we start to dig deeper into the problem, we can say, okay, any component when it is loaded by a few specific load modes. This can be torque, this can be bending, this can be axial loading, push-pull. And whenever I combine these effects, it's very likely that on the surface of the component, I will get the maximum stress. So technically for me, it means that if I want to analyze what is the fatigue life of a component, I should focus above all on the surface. There are exceptions, and interfaces, integral defects, forced on parts because of the surface is loaded. That means also contact surfaces, or any cases where there can be residual stresses. I here wrote also take care of gigacycle fatigue because of there. Anyway, the crack could be initiated out of the surface. So that means surface is something what is interesting for us for multi-axial fatigue analysis. And if I check the common state when it is non-loaded surface, it means that the normal stress in this perpendicular direction to surface is 0. The same for shear stresses acting here along the surface. Yeah, so here the shear stress, here the shear stress will be also 0. So we have a plane stress state. And if I draw more circles for this case, here I have the 0 of the surface. And based on the loading, I have some combination of other normal stresses and one shear stress acting. So I will get these Morse circles. And based on static hypothesis of tensile strength, I can say, okay, this is a point of interest because of there I am reaching maximum shear stress. And it is inclined, this plane is inclined from surface by 45 degrees. And then the second point of interest is where I reach maximum principal stress. And again, from free surface, it is inclined by 90 degrees. So already now I have some expectation that there are some specific planes where I should look for potential cracking. Because of if I start with analyzing, I can say if the crack is very small, it's really tiny, it's just to start, it's of planar character. When it starts to deviate, it starts to change the direction, but at the very beginning, it's a plane. And that means the load state description on that plane should be the primary input for any my analysis of fatigue damage. And what is important, shear stress parameter usually is expected to play the dominant role. It is governing the crack calculation. But if there are any normal stresses acting simultaneously on that plane, they can have a secondary, still important effect because of they can open the created crack or they can close it. So if we accept that we should look for specific planes, the previous slide with Morse circles showed you that for plane stress, we have two sets of candidate planes to be analyzed. One set of planes is perpendicular to the free surface. This is the left case here. And the other set is inclined by 45 degrees to surface or to normal to surface. So these are candidate planes at which I should look for stresses. Now, if I start to look at specific planes for acting stresses, again, we have those two types of loading, proportional loading and a non-proportional loading. For proportional loading, I can, or for both cases, I have to split the original stress vector to normal stress and shear stress. For proportional loading, because of it doesn't change direction, it means that not only normal stress, but also shear stress is still running across the same direction. So it can change the magnitude, but the shear stress vector will show will point still in the same direction or opposite. In case of non-proportional loading, yeah, normal stress stays normal because of that's by definition of the stress. But the shear stress can start to show in different direction because of it changes its position or its direction. And if the loading is periodical, it can happen that the endpoint of the shear stress vector will start to draw some specific closed shape. Yeah. So shear stress starts to rotate. And now, if you remember the previous slide, we believe that the primary role in fatigue damaging will be attributed to shear stress. It's of a higher interest for us, how to evaluate it correctly. There are different ways of solutions. Again, here, this shape here is a set of endpoints of the shear stress vector. And the oldest solution was to make a longest projection method. You are simply looking how to project this shape into a specific direction. From that, you will derive shear stress amplitude here and here. And because of this is a projection to a specific direction. Only this is shear stress in the mean value. Then came a bit better solution because of this downplayed the role of shear stress, of the mean value of the shear stress. The second possible solution is to use longest chord method. That means I'm looking for a pair of data points which are producing the longest shear stress range, or half is amplitude. In that moment when I find it, I say, okay, this is my midpoint, and to that the mean shear stress is pointing. That means I can compute mean shear stress more precisely than here. There's a problem. There can be geometric shapes, for example, isocels, which produce you different mean stress values based on the different chord, which is still of the same length. So today the most common solution is to use a minimum circumscribed circle method. That means you have again the shape here of the shear stress endpoints during the period, and you are trying to enclose it into a circle of the smallest possible diameter. So the radius of this circle is amplitude of shear stress, and the midpoint of the circle is showing you the mean shear stress. While in Brazil and Portugal, colleagues started to claim that it's an imprecise solution because for this shape, for this circle, or this line, it will produce all the time the same shear stress amplitude and mean shear stress values. So that means there would be no effect of out-of-phase loading at all. So they proposed, okay, we should make it better. Let's make the enclosing shape an ellipse. So here you see a solution. In comparison to that, they are not choosing the shear stress amplitude as being the bigger semi-axis. They are combining both semi-axes together to produce the shear stress as their product. So you see there are different solutions for defining the shear stress amplitude and mean shear stress value if I need it. The question is, I conditioned this analysis by the fact that this is a periodical loading. How often in practice you will encounter periodical loading? That's not very common. It's good for experimenting, for verifying, validating methods, and so on. But in industry, it's very uncommon. So the question still persisting here is how to get the cycles. Commonly in uniaxial space, we are dealing with rainflow analysis. That means we have some continuous load history, and we will convert it into a set of discrete cycles. The question is what we can do with non-proportional loading. And well, again, as engineers, as we were prone to use von Mises solution or principal stress solution, the easiest way is to use rainflow procedure just on some products, for example, on normal stress, because if it doesn't change the direction. On the result shear stress, pointing into a specific direction, or on some built-up equivalent parameter. The question for me, myself, is, well, originally the idea behind rainflow was that in every closed hysteresis loop, we are enclosing some strain energy density, which is directly related to the imaging process. So that it makes sense. But here we see projections into specific directions. The strain energy density is enclosed just in specific direction. And the question is if the loops are closed at all. How you recognize in a multiaxial space of 6 components that the hysteresis loop is closed. There are more complicated methods. Currently, I'm aware of two. One ground solution from 96, We have tried to implement it, and we do not believe this is a best solution today. But, this is the best solution because there is no other. But basically, if you are from industry, I would like to say that we do not have anything proven to work well for this part of the complete multiaxial fatigue strength or multiaxial fatigue analysis at all. There is a point here, no decomposing at all, concept of continuous damaging. Professor Stefano from Bulgaria for a long time used to work on that, but today he's already retired. And the website at which he proposed the implementation is already gone. So technically, this is a vast space for analysis. The issue is that you will see it later on. It would be nice to dig in deeper, to analyze for different load histories, what is the perfect result, but we still cannot unite even on the question what is the right damage parameter. Hidden part of the text. So this is about different families of multiaxial fatigue criteria. One of them is critical plane approach. Basically, I will check the damage parameter on different planes. For example, those candidate planes proposed by Banantine and Sossi. And I look for the maximum of some parameter, damage parameter, some stress parameter, whatever else. And when I reach it, I say, okay, this is my critical plane. There, the crack initiation will start. And I'm focusing all my analysis just to this specific plane. And you see there are different solutions for that. I will mention the concepts behind them later on. So here you see we are focusing our attention to one specific plane if I evaluate one specific point. There is another type of solution, and this is some so-called integral approach. Because of there, I compute the damage parameter, if possible, across all planes. That means I have to discretize in some way. And I will make basically average across all possible orientations of the planes, which is technically done by space integral of all damage parameters across all planes. And there you see some proposals by, for example, Papadopoulos, Kenman, and others. Averaging is basically integration. And what is interesting today, most practical implementation concerned only critical plane solution. Integral approach is, say, still mostly related to research, and nobody is trying to implement it. And my question for a long time was why it is that way. We have dealt a lot with that question, and in one moment we did comparative analysis because of, for both concepts you have to go through different candidate planes. In one case you are looking simply for a maximum value. In the other solution you are integrating every other occurrence of the plane result with the previous values. Yeah, you are averaging the content. And my question was, what I expected is that people can imagine that the search for a critical plane solution is something to be easily optimized. You do some per scan, then you dig deeper into positions where you see current maximum, and based on some gradient approach, you can get to the peak, to critical plane. For integral solution, I cannot simplify it in any way. I should go through those per-selected planes and to integrate everything together. So I expected the reason why everything today implemented is critical plane solution is because of people expect integral solution is more complicated as regards the requested time. We did this analysis with all data we had. And just here are the most responsive test cases. We checked if we start with something like 5,000 candidate planes, and we start to decrease the number of planes evaluated for integral solution and for critical plane solution, when there will be a break point at which the results start to be worse. And you see, if you compare that for integral solutions, I can get to lower number values of candidate planes. So technically, in that way, it's indirectly proven that the stability of integral methods, once I need to quickly compute, is better. Now, if we compare the critical plane solutions, we have the most frequent families of the criteria are questioning what is the way to describe the plane as critical. Yeah. And one of them is to look for maximum shear stress amplitude. So I'm not looking for a damage parameter for some equivalent stress. I'm simply looking for a plane where is the maximum shear stress range or amplitude. The issue is that one large shear stress amplitude on one plane can be the effect, the damaging effect can be much worse if I create less damage on another plane just slightly aside, yeah, but with many cycles. So for me, this concept is to be abandoned, despite that many people use it. Sorry, there is some bug. The other solution is maximum damage analysis, which looks for. Sorry for that bug, for maximum damage parameter across all possible candidate planes. So for me, this is the only acceptable solution because of it's more realistic. Anyway, if I compare a critical plane approach and integral approach, it's fascinating that they have so different philosophy. In critical plane approach, I'm looking for a shear maximum. Only the maximum value is of interest for me. In integral approach, I integrate the damage parameter across all planes. So one would expect that the results of both types of criteria would be substantially different, at least for some cases. And I have to say that until this moment, we haven't found this distinction. If you have a properly set critical plane approach, you can get a very similar quality of overall results as for integral approach. That's something which is surprising and a bit bewildering. Then there is a third family of criteria which is based on enclosing the load path in the Ilyushin deviatoric space. I will explain it. Oh, sorry, that's not what I wanted to do. Okay. You can split the stress tensor to two parts. One is hydrostatic stress here, and one is deviatoric stress. And if I transfer the deviatoric stresses to a 5-component space, as defined here, it's called Ilyushin deviatoric space, I can combine this second invariant of shear stress deviator with the hydrostatic stress in some way, in some weighted addendum, and use this as a criterion of fatigue strength analysis. And the advantage of this solution is that the critical plane methods and integral criteria ask you to deliver the results on very many candidate planes. If you have to use the minimum circumscribed circle algorithm, this is again some optimization routine. It costs you a lot of time. But with Ilyushin deviatoric space, you have to do that, for example, minimum circumscribed hyperbole method algorithm. You have to run it in 5D, in 5 dimensions. But this is a common procedure which is simply mastered by computer, and you have to run it just once, compared to previous hundreds or thousands of evaluations in the previous case. So it's much quicker solution if it would work well. What is interesting today, if you compare what is implemented, this table is a bit obsolete today. For example, here LMS Virtual Lab is a part of Siemens SimCenter, for example. MSC Fatigue is not anymore MSC Fatigue, it's redressed into CIE Fatigue by Hexagon. But anyway, it still shows what is the common distribution of different solution methods across different fatigue solver packages. And you see that if you check this table, that most of the solvers uses Dangwan solution. Some of them use McDiarmid or Findlay, and to much lower extent there are other methods or even a proprietary solution by FABER. And if you compare the quality of the results, that means mean fatigue index error for the large data set, for the standard deviation, you will see that, okay, the Dangwan solution seems a reasonable choice from this selection because of it has very moderate deviation from perfect mean value, and the standard deviation is one of the lowest. If I would go to McDiarmid, I can have even smaller standard deviation, but the criterion would be shifted in overall results to non-conservative side. So here it seems Dangwan implementation is something quite tempting. It's a reasonable stuff. If you check how it is formulated, you see that this is basically a shear stress amplitude weighted together with maximum hydrostatic stress compared to fatigue limit or fatigue strength. So it's basically a critical plane criterion in one of its versions. It also has its own definition in illusion diametric space. And today is most often used representative. You see the histogram here is definitely much better than von Mises or maximum absolute principal stresses. Yeah, you see nearly all data got into the range between minus and plus 40%. The issue with this solution is that it has its weaknesses. Here you see it compared on the results of our data set. When I selected just cases without any mean stress, so that it doesn't, we needed to bother with this parasitic effect. So without any mean stresses in out-of-phase loading and in-phase loading, you see that there is very distinct difference between the mean value of the whole data set in fatigue index. And that's surprising. This should be a common tool for multiaxial fatigue analysis, but if you apply the basic condition out of phase loading, you are generating substantially non-proportional results. When I was presenting my analysis validation of different multiaxial fatigue strength criteria in Milano, 2010 or 9, a colleague from there, Mauro Filippini, came to me and told me, I know about the perfect criterion from America. Simonson McKnight implemented a solution which has very similar results to Dangwan. So when I returned to home, I checked that. It's basically very simple. It's again technically a von Mises, if you see that. But this von Mises criterion is not evaluated in every instant. But instead of that, you have to know what is the cycle. If you know where the cycle starts, when it ends, you run the analysis to get amplitude and mean value of every stress component separately. And then you build the composite amplitude and composite mean value from these components in amplitude and mean values. And here you see the results. This is a comparison of the histogram of Dangwan and of Monson-McKnight. Dangwan asks you for a quite tedious iterative algorithm, something to be implemented. Monson-McKnight can be solved in Excel spreadsheet without a problem. Dangwan asks you for your time or for 5,000 euro to buy it somewhere. Monson-McKnight doesn't ask for anything. Yeah, you have to buy spreadsheet calculator. So technically, it's much better than sine for mesostress, but it has some weak sides, some disadvantages, and you cannot know them unless you have a proper validation basis and benchmark set. I had that benchmark, so I ran analysis comparing Dangwan and Menzon-McKnight in mean values, in ranges. This is difference between both values in all cases, in ranges, in standard deviations. And based on that, I could see that in some cases, Menzon-McKnight was a perfect solution. For example, here I have a biaxial loading without any phase shifts. There, if I use Dangwan, I will be completely conservative in mean value. I will have a large standard deviation in addition to that. But if I use Menzon-McKnight, moderate mean value of the fatigue index error, and much lower standard deviation. So technically for pressure cylinders, yeah, it's a perfect tool without the need of very specific complicated fatigue analysis. But if this pressure vessel was set, for example, to move and to generate, and more different load cycles could be generated, not just the pressurizing itself, you see that if I use the same concept of biaxial loading with non-zero mean stress and in addition with phase shift different from zero, Menzon-McKnight criterion quality deteriorates very quickly to very ugly non-conservative mean values. And in that moment, I would be happy to pay for Dangwan to have it completely correctly solved. So, well, Dangwan is today something to be implemented, something implemented everywhere. And the question is, if we cannot get better results. Just here a small deviation. We try to propose a better solution to supersede Menzon-McKnight by MMP criterion. You see that we end up with different results. But one of the guys here in this meeting has a much better solution, but he still didn't proceed to publishing it. This MMP criterion has bad. There's an error in expectation. It's not invariant, so it depends on the coordinate system you used for its computation, which is something which should not be allowed. So because of that, we should look for a replacement with a better criterion. Now, I just wanted to quickly go through other histograms of other today implemented criteria. This is McDiarmid. It's a combination of shear stress amplitude and maximum normal stress with some weights added here in addition. And there are two different implementations. You can use it as a maximum shear stress range criterion or the maximum damage criterion. Here you see the results of damage, which are better, mean shear stress values. And here you see the parameters. Technically, it has better standard deviation than Dangwan. It has much smaller range, but you see that its average value is skewed to the left side. So it's more non-conservative than we would like to have it. Here is a Findlay solution, a very simple criterion, basically very similar to McDiarmid. You see the same set, but the parameters A and B are different from the previous one. It's only an MD type solution, that means maximum damage solution. And you see in this moment, histogram is also relatively nice, but the standard deviation is larger. And it's skewed to too conservative side. Then there is a Crossland solution. And by the way, Sinus uses the same criterion, but here is a mean hydrostatic stress. So this is of the Illusion Divateric space family. Here you see the second invariant of the shear stress deviator. And you see the results. I would say quite similar to McDiarmid, but with smaller standard deviation. but also again with two non-conservative mean values. And here you see something completely different. This is a criterion which I proposed now already 17 years ago. And I guess you immediately see that we are getting to standard deviations which are half of Dangwan method. The range is also awesome, average very nice. It has some weak points. I will mention it later on. Meantime, we published here in this paper even improvement, which allowed us to get to a standard deviation of 5 for the whole set, and to arrange results of 31%. So I was quite happy with that. But a colleague of mine, Andre Berne from Norway, came to me with a proposal for a joint paper, and during the discussion, he found out a bug. So whoever would like to use PCR or PCN criterion, take care. Because of here you see a common multiaxial load combinations for data tested by Anes and Reich. And what he defined here as augmented sets is basically push-pull loading here, the first case, augmented one, which is decreased to 1/2 of the fatigue strength, of the fatigue limit. Yeah, so that means we would expect that with this loading, the criterion should result in 0.5 in fatigue index. And then he did it with shear stress loading. Again, this is a half of the shear fatigue limit. And then he did it in the opposite direction, and he multiplied by 2 and 2. And here are the results. For Duncan criterion, these augmented sets generate fatigue index error of 0, 0, 0. But here with PCN, with that criterion of mine, we are getting to very non-zero values. And the same with an integral criteria PIN. The reason is here. In this square root, in this formulation, you see that we have a quadratic section of shear stress amplitude and linear value here. Because of this is linear, it means that the BC parameter is not unitless, but it has a meaning of stress. This is unitless, but this is stress. And specifically for this formulation, it's directly equal to fatigue limit value. And now imagine what happens if I put this, I will invent a new formulation where there is a square root here. That means in that moment, BC will have to replace the missing shears, the missing stress, and it will be a quadratic value. Oh no, something more ugly. It will not be even quadratic, but something related to quadrate of original material parameters. And that's the issue, because of in that moment it means that this material parameter helps the criterion to reach perfect unity. The deeper I would go, the more different would be this as regards the power over this parenthesis, the more affected would be BC, which would be in that moment more identical to what I request. I request here fatigue limit. So here would be fatigue limit, and that means this is the reason why for 0.5 desired fatigue index, I am getting to much more conservative values because of the criterion tends to provide me not 0.5 but 1. And here again, though it should provide me value of fatigue index 2, no, it provides me something smaller because of it cannot get to this value. It tends to go to 1. So technically, this is something what we call a prediction bias. And for me, it means that this PCR criterion should be abandoned. And we published it like that. To get out of the problem, I had to resort to another criterion of my provenience, which is a bit worse, but it doesn't suffer from this prediction bias. You see here, this is QCP. It doesn't suffer from that simply because of this is a quadratic formulation of shear stresses and quadratic formulation of normal stresses. And yeah, the range is bigger. Standard deviation is alpha 6.7 compared to Dangwan's 12, but you see it's definitely better. So what I wanted to say, I could show you here histograms of very many different further multiaxial fatigue strength criteria. You see some of them here, just some of them. These are different methods. Here is their overall evaluation with standard deviation, mean relative error, number of occurrences in different papers in Fatigue and Fracture of Engineering Materials and Structures and International Journal of Fatigue from 97 to 2015. In that moment, these methods were evaluated in these papers. And I highlighted by gray background those methods which are today implemented in fatigue solvers. And if you check the results here, above all the standard deviation, isn't there something striking? Technically, those which are today represented in practice, which are provided to engineers to be used, provide the worst results overall because of the standard deviation here is not beaten by anything else here. It's the worst one. Maybe here, Liu and Mahadevan criterion from 2005 has similarly bad results. And it's something very surprising. And this is also the reason why I initiated Project FABER, because we need to make the fatigue estimation more reliable. Meantime, in previous years, we have published, for example, here a shortened benchmark set. If you would like to invent a new criterion, go forward. Yeah. But I recommend you to use this because of there is complete data set of about 50 data items which you can use to try to propose something new as regards the fatigue strength estimation. Here we have published very many explanations and comments regarding to multiaxial fatigue analysis, how to benchmark the data, what are the good data sources for analyzing. But anyway, if you would be interested in that topic, I would recommend you to join FABER consortium. This is the best solution to get to this data set because I will publish it there. Oh, sorry, what's happened? And there is some bug. The last paper here is already mentioned. It is the paper by Andre Beme and me concerning the data set, the data prediction bias. But in addition, Andre defined there his own integral criterion, which reaches very similar result to QCP method. So again, the same situation happens. If I have properly set damage parameter, I can get very similar quality of prediction result if I use integral solution or critical plane solution. I have to say, for me, this is a bit disparate situation because of it shows me that basically we are still just curve fitting. We are just trying to get the best possible solution for a given data set, but it's not related at all to the real description of how the damaging is induced in the structure. It's just a quick engineering approach, not big science. What I wanted to mention here as well is another analysis which we published. For a long time, when I was above all dealing with my PhD thesis, I was surprised by people who tend to say contradicting expectations. Some of them said that if I have in-phase loading with given normal stress and shear stress, and I use the same stress amplitudes also when the loading is dephased, for example here with 90 degrees phase shift, I should get lower lifetime. Now I should get higher lifetime. Yeah. And well, it was obvious that there is no consent. I have tried to gather from my experimental data, or from those which I gathered, to see what is the response if the theory is like that it extends fatigue life, or I mean dephasing of the load signal extends fatigue life or shortens it. But I have found out that the experiments are on both sides of this. Yeah, that in some cases you can get longer lifetime because of you have a phase shift between both load channels. In some cases it's vice versa. And here, just for you to understand, I built a metric which say, okay, fatigue index obtained for out-of-phase loading with the same amplitude, and to fatigue index obtained in-phase loading. If it is higher than 1, what it means? It means that the dephasing of both signals should increase induced damage. Yeah, so that's the interpretation. And now look at these graphs. What it shows is that we have here perfectly in-phase loading, and here fully dephased loading by 90 degrees. And you see the same integral criterion. Lewand's quite famous in Germany above all. And what differs between those graphs is that in this case, we used minimum circumscribed circle solution to derive shear stress amplitude and mean value. In this case, we used minimum circumscribed ellipse, and here we used something completely different. Moment of inertia proposed by colleagues from Brazil, Migelar and Castro. And because of they believe that dephasing should for sure worsen the fatigue life, all the data there show that for dephasing, I'm getting much higher out-of-phase damage. On the contrary, if I use the same criterion, but I use minimum circumscribed circle, most of the cases will stay below that. That means dephasing is basically mildly positive because of it decreases the induced damage. And it's surprising for minimal circumscribed ellipse, I am getting to indifferent results. It doesn't matter if I have phase shift or no. And you see, what is for me very important is I'm using the same damage parameter. And this distinct difference in the quality of the prediction is caused just by a tiny part of the multiaxial fatigue criterion, how to describe shear stress path in out-of-phase loading. And for that reason, I say, okay, if you would like to invent a better replacement of rainfall analysis in multiaxial space, that's awesome. But unless we understand these tiny bits of multiaxial fatigue analysis, I'm not sure you can get a reasonable output. Here, just shortly, I will make a short look into low cycle fatigue, just for you to understand, because of the concept is still the same. Yeah, here is description of the test which we use just for some initial validation. I must admit that low cycle fatigue is not my cup of coffee. Yeah, so here you see different load paths, specimen, structural steel, and here you see Saucy proposal. What he does basically is he compares two different crack initiation modes. One is in shear, for shear stress crack initiation, and here he combines maximum normal stress with shear strain amplitude. to use Manson-McKnight formula for shear stress loading or shear strain, control shear strain loading. And in addition to that, he looks for another pack of evaluated planes where he uses modified SWT, Smith-Watson-Topper criterion, simply multiplication of maximum normal stress and shear strain and normal strain amplitude. And you see basically here that for our data, we've got into a range of 10 multiples of lifetimes, which is not a very good result. But definitely the data are not following our expectation. We are out of the bound of typical publications between of multiple Fourier. So Saussuyer's model is nothing special. It's again the same concept of critical plane. And here he proposes for using high cycle fatigue cases, something which is technically Findley criterion, nothing else. It's again Findley criterion, combination of shear stress amplitude, combination of normal maximum stress, and related to Basquin formulation of shear stress control loading. Nothing very special. And if I compare it with another method, this is Wang and Brown solution. And again, the damage parameter here is technically some equivalent shear stress amplitude, because of this is a half of range. And it looks for the stress signal, or sorry, for the strain signal, and detects what is the half cycle of each shear strain record. Once you have the half cycle, you will look along this half cycle, what is the maximum normal strain and minimum normal strain, and you say, okay, this is my effective normal strain, which I used for this damage parameter. And again, this is nothing else than Manson-McKnight, Manson-Coffin formulation. Here is the damage parameter. Here is shear strain amplitude, so I can put it together, get fatigue. And here you see results. There is a modification by Kim, Park, and Lee on the right side, where they believe that instead of checking the effective normal strain just over the half cycle, you should do it across the whole cycle. And technically, for the data which we had, they are a bit more effective. That's all. Basically, it's not that different from high cycle fatigue analysis, just you are using strains, which makes everything much more complicated, it's true. But otherwise, there is nothing very special. The critical plane solution is leading here. I'm not aware of any integral type definition for low cycle fatigue analysis. So if I try to sum it up, multiaxial fatigue analysis is interesting, but it's here for a relatively short time. There are many more interacting effects. I mentioned just one of several of them. Take care, for example, of that shear stress path analysis. That's something which was not understood 5 years ago, that there is an issue. The numerical analysis is much more complicated. It's still unclear what is to which concept to relate the damage initiation, why integral methods and critical plane solutions provide you the same quality of results if properly tuned. There is a vast number of criteria. We have published another paper summing up some recent 6-7 criteria and saying that the older ones are technically better. And still, despite of this lack of quality, industry needs that, or they would like to have something, because of you have to understand it's not about just multiaxial loading. It's also about analysis if you are using finite element data. And there, in any notch, you have a multiaxial stress state. So to have a proper solution for multiaxial fatigue analysis is of quite big interest. And it's not here. I would like to thank for the support and also to COST. They supported us with this public public presentation of current results, which preceded cost, I have to say. Please, I will go to the very first slide where you have my contacts. I will stop recording, and just because of I'm in a bit haste, I would like to ask you to write me in any case you would like to know more, if you would like to join us in a FABER project. Do not hesitate. The ways how to contact us is also here on the website. So thanks for joining, and that's all for today. No discussion session. Sorry for that. So bye-bye.
Bye.
Thank you. Bye.
You're welcome. Bye.